Yeah, how's it going, everyone? It's Mo here. So this video is about building AI for the places that the network doesn't reach. We're talking about environments where there's like no cloud access to the no cloud access, no retry. Basically, we're talking about hardware that you can't touch once it's out there. So just a quick background about me. So for the last decade, I've been building machine learning and mission critical systems across industries. And specifically for the last 7 months, I've been like fractional CTO for defense, like tech defense startup, and we'll be building like a system that exactly matches this type of video. So this is like some reflections, some pattern recognitions from my past decade specifically tailored to defense sector. And we're talking here about places where being wrong isn't just like simple bug that you can fix in the next sprint. Something that it's actually a real problem to cost a lot of money and even like people's life on the risk if it's wrong. Um, so just like summarize something here because this type word actually force you to think about something underneath the surface. So basically, like when you can't lean on bandwidth or clean data or just like do over type mentality. That's which is like so common, especially like now for AI engineers. You start like to see what actually an AI model or machine learning model is actually is, and once you see that, there are like four main things that like you cannot engineer way out of that, no matter how good your shape was gonna get. So this video isn't just like some checklist. It's actually like one fact about what an AI model actually is from this specific perspective on hardware where there's no access to the cloud, and also like the four consequences that fall out of this. And just like by understanding the fact here, you can work out the right call for your own system, which I'll never gonna see, but you can see. So this is not something like I'm gonna give you some example and tell you do this and don't do that. I'm gonna give you the tools so you can think and engineer your way to solve your actual problems here, which would be more helpful here. So um, just like quick thing here, just to make sure that this actually for you and this will not like waste your time here. So this is for you if you actually ship AI into the real world, and you're actually the one who's deciding how it's gonna build. And basically what you want is you want to understand the machine and not just like get handle list of random rules. And this is not for you if you're building some cloud product with like some maybe OpenAI wrap or stuff like that. It's not for you. You can leave the video right now. Um, Also, like if you're building any type of AI systems where the network is always there and you can just like always retry, this is not the best video for you. You can go check another videos. Basically, like if the honest answer to your problem is just like call the API again, this won't help you at all. So now the only people who would care about this video stay. So let's move on. So let's start by talking about the common fact that everything comes from. So if we're gonna render everything to like first principles and all, and we're gonna think using multiple mental models, what we're gonna find is like a model is actually geometry fit to actual data. That's it. That's what's actually like an AI model is. Basically, it learns the shape from the example you show it, and everything that isn't in those examples, like everything besides that data, or maybe like past it, or maybe underneath it, just like gets filled by the structure of the actual AI model, and not by any type of like external knowledge. Not like something so knowledgeable that would understand stuff that it has not learned. And I wanted to hold to that point specifically because basically this is like what this whole video is about. And based on this thing, there are like main four consequences that would fall straight out of it. So if we're gonna talk like past the data, The model extrapolates, and beside the data it's gonna throw away most of what you think it's gonna look at, and underneath the actual computations there's a shared bus that decides everything, and and for the place that where it was never trained, its confidence is actually undefined, so basically it's unreliable there. And these are the four consequences, and just like one fact here, so let's take them one at a time and actually go under the hood on each one to understand how what that means, how it actually works, and how you can actually prevent issues from happening there. So let's start by the first one here. So for this consequence, it's consequence one. It's talking here basically this consequence means model doesn't fail outside its actual data. It's gonna extrapolate, and that's super different. And actually, it's much more dangerous thing here. So this is a simple visualization for you. And now let me show you what actual network actually is gonna learn. Because the if we're gonna remove all that complex math and just render it to first principles and thinking through mental models, it's way simpler than most people would think here. So I wanted to look at this simple visualization here. Basically, neural network, which is we're talking about the standard kind of neural network, is basically just stack of linear maps with simple on and off switches between them. That's it. And what that actually does is if we're gonna talk geometrically, it's just gonna carve the input space into regions, and these cells that and these basically are the cells that you're looking at right here. And here's the key part here, because inside each of these cells, the model is basically a straight line, so it's linear, simple, predictable, and the training's whole job is to actually draw these boundaries and set the slope inside each cell, and doing that and using the data to do that. So in other words, trained model isn't some smooth magical surface. It's just a patchwork of flat pieces, and these pieces would gonna fit the examples that you're gonna give it. Now I want you to watch what happens at the edges here. So here's the actual data. So this is the dense region in the middle here. So the training set let's see, training set slopes are actually here, where the examples actually were. But I want you here now to look at the cells out past data region. So as you can see, they don't stop. So the flat pieces just extend outward, extended forever, and they follow whatever slope the nearest data happened to be set at. So in other words, there was no data out there to correct them. So what's gonna happen is the slope is just an accident, and it's actually whatever the training is gonna left behind. And now let's talk about actual real input comes in from the field, and actually it lands out here in the unanchored space. So the model gives it a confident answer, but the answer came from a line that was fit to something else entirely here. So if you're gonna see, it's not actually a guess that the model knows that that's actually a guess, just like the model doing exactly what it always does. So what that means is the model is gonna always apply flat rule, And I want you to expect like this rule was never anchored to anything for this example. So basically it's gonna hallucinate, it's gonna guess something, and he's gonna believe that he's right. And here's the part that actually should stay with you for this first consequence here. So this curve is actually the model, and as you can see in the middle here, so between the two data points, it's interpolating. So what's gonna happen is it's actually is gonna fill the gaps between things it actually saw, and that's actually reliable, and that's what actually the AI model is good at. But out here, just like past the last data point, just like it's gonna extrapolate, and just like it's gonna continue the line forever. And I want to look at the two here. So basically, like for us, if we're gonna just like standing outside, what's gonna happen is like we're gonna see like one is safe and one is dangerous. But same thing like if we're gonna put ourselves in the AI models lenses, it's actually the both of these are actually identical operations. Uh, all it does is just like it's applying the same flat rule in both places, and thing is like there's no boundary it's gonna cross between them because they're identical to him. So what happened is like there's no moment where it's gonna go and gonna say like, I need to be careful now because I'm past my data, because nothing's gonna light up for him. It's the same thing. In other words, well, or what that actually means here is like falling outside is data. For him, it looks like from the output perspective, exactly like succeeding inside it. So it's like the same confidence, same everything, and for us, this is like the whole danger here, and that's like what causes hallucinations and many bad stuff that we cannot afford, especially in such mission critical systems, or like in or even like if we're gonna put it in hardware where we don't have access to the cloud, or we cannot like just simply do a retry and everything's gonna fix. For this environment, this is so critical to understand. And basically, this architecture of the model is built into the geometry of the model itself, so we need to be aware of it. Now you may be asking like, now we're gonna talk about the decision itself here. So, and for this one, you don't need me to hand you some specific rule or give you like do this or don't do that. So let me help you understand this point better, which is about the accuracy number. So for the accuracy numbers, it's gonna measure the model where the data was, and we're gonna measure it inside the anchored cells. So in other words, it's not gonna tell you not anything about the cell that your field input actually lands in. So in other words, like a number without the distribution, it was just like measured on weak information. So pretty much it's useless. And the lever falls out too. So if we're gonna talk about like for example, if the problem is that the field lands in an anchored space, then you fix it by putting the field distribution into the training data, and you're gonna anchor the cell. So now what's gonna happen is like you're not gonna extrapolate it, so the model is not gonna extrapolate anymore, and it's gonna start like interpolating, because now it's already like seen that region again. That's like the whole point here. Okay, now let's move to the next consequence of that, which is like the model doesn't read your input. What it actually reads is compressed representation of it, and this what that makes is like this is gonna change what the cleaning up the input even means in the first place. So As you can see here, I wanted to follow the input through the actual model and what's gonna happen exactly. So let me just like, yeah, like this so you can see everything. Okay, so as you can see here, like the input's gonna come in as pixels on the left here. And I want you also like to watch here each layer and what each layer does here. So layer just keeps the stuff that's useful for the specific tasks, and is gonna throw away the rest of the input. And then what's gonna happen is like the next layer would do that again and again and again. So basically, like the representation gets narrower every step. The reason of that is like because each step is actually discarding what it actually learned, it doesn't need, and keeps going forward. So what that actually means, like by the time you reach the decision layer, or let's say the output of the model, which is like here on the right, most of what you and like what most of what like you and I would call the image is gone, and what's left is that like this only small set of features that the model happened to find useful for this job, and that may be right, that may be not right for that specific case, and basically just like with that small set of the information of like that small set of representation of the actual input to decides on, and not like the whole picture. So this is like if we're gonna render it back to first principles, basically the reason of this is like the just like compressed things. That's like what caused this issue to happen. And now let's talk about why this actually matters in like real life, and especially like in such environments that we're handling. And this is like the part that most people like, and let's say 99% of people won't account for it. So if you're gonna see here, like there are two different spaces. So on the left you can see like the pixel space, what you can actually see, and on the right is like the feature space, well, which is like what the model actually reads after all that discarding. So if you're gonna like take two inputs, let's say A and B, in the pixel space, which is like here on the left, they're just like right next to each other, and on that layer, like they're gonna look almost identical to you. But if you're gonna take it to the and we're gonna check it from the feature space, which is like here on the right, then these like to same points, like point A and point B, can be way far apart. And the reason that, and also like because like the model kept different feature for each one, so that what causes these to be far apart from what they actually are. So like distance from the training data, which is like the things which is gonna decide whether you're in an anchored cell or not, is distance in this right hand space. So in other words, like the space that you cannot actually see, and like two things that may look identical to you, like, or at least like almost identical to you, can be like weighted so differently from like the machine learning perspective, which like made them like completely in different regions, which make them like so distinct to the model. And now let's move on and actually put that against the instinct to maybe just like we need to clean up messy input with simple denoiser that would fix things, right? But in reality, what's gonna happen is because I just like show you the pattern here. So what's gonna happen is like the denoiser will just like optimizes the left space. We're gonna talk, which means like the pixel space. So this place, yeah, that's what the gonna denoiser gonna optimize, and basically how it's gonna look. So but in reality, like the actual model is gonna decide on the right space, this space. the feature space. So we're talking about the features. So basically, like when you're gonna clean up the pixels, you're just like polishing the exact information that the model already threw away. So basically, like while and what's gonna happen is like it's gonna just like blindly move in the features. It actually read here, in also like in a direction that you cannot see or predict what's gonna happen. So that's why I like to get the thing that sometimes like make no sense on the surface level. So reason of that is just like the image quality or the pixel quality just like goes up and the accuracy goes down. So basically like these two are two different spaces, and the noiser won't do anything to fix the feature space here. So for this one, like you basically like you got two different ways to close this gap between your model or what your actually model actually reads and understands, and your actual messy input. So what you should do here is actually like you need to move the input toward the model, and basically like if you're just like gonna clean it, which is super fragile, and maybe like you're so blind to whether that worked or not, as I explained to you for from the features perspective. Basically what's gonna happen is like maybe you're gonna train it on a mass, which gonna reshapes the feature space around it. So so like the only way to actually know for sure, like certainly, um, what you actually got is you need to measure the whole chain here. We're talking about like end to end, not just like focusing on the pixels, a layer, because things like you cannot see the actual geometry that matters to the model, which was gonna use to make all the decisions and all the and producing like the desired output for you. Okay, now let's move to the next consequence here, which is like consequence 3. And this one is actually based on pure physics here. So if for like fixed hardware, your latency is not like set by computation. It's actually like the thing that is gonna like decides the latency is the moving bytes themselves. And once you can actually see that, then like the fourth thing that you're trying to optimize is gonna like turn out to be just like one thing. So in other words, this is how you can actually understand like what causes the latency not to be desired one as you expect from your system, and this is how you can actually fix it. So first of all, let's talk about the shape of every like accelerator. So as you can see here, this simple visualization here. So with the flat line here, like up top, this is like how fast the chip can actually do math. So in other words, it's like really high, and especially now like modern chips, like if we're gonna talk about Nvidia chips and all their like monsters when it comes to arithmetics. So there's no issue when it comes to that. And as you can see here, like this rising line, this is actually like how fast it can fetch numbers from memory. And here's like the thing for most models. So basically, like for most models, you're just like gonna operate down here. We're talking about like the memory line, which in other words means like the compute units up top are just like sitting there idle, they're not being used. So basically like this gap between like this gap here is just like your processor just like keep waiting, and just like it's gonna keep waiting for the data to arrive, which is like it's gonna take a lot of time. So in other words, like the real cost of running your model isn't the actual math here. So the math is basically free, and mostly it's idle. So the actual real cost is actually moving the weights and the activations across a fixed amount of memory bandwidth. And that like your basically the issue is like your memory bound, not compute bound. So the latency is not about it's not like the issue of latency is not you cannot solve it by focusing on computations here. And like almost like everyone budgets this like the wrong way and focus on trying to solve computations, trying to add more computations without acknowledging the memory bound itself. Okay, now if you're gonna see this now from the byte perspective, so as you can see here, like once like it's bytes across a bus, I wanted to see exactly what happens to your four goals on how you're gonna like improve latency and all of that. So this simple visualization or animation can explain a lot here. So here on the left is the actual memory, and on the right we're talking about the computations. And this between the like the memory and compute is the actual like this is like the channel between it's like the actual fixed bandwidth. So what's happening is like everything has to cross it, going like from memory to computations, and it's only like moves so many bytes per second. And now I want you like to look at the four things that you actually want. So what you want is actually like a more accurate model, which is usually bigger model, which in other words means more bytes to move. You want lower latency, which means like fewer bytes per inference. Um, because like your memory is like a footprint is literally is the bytes themselves, and basically like your power is dominated by moving those bytes, not by the computation itself. So in other words, like the four main goals that you want, they're actually they're not independent. There's just like like four different views of one same thing, like of the same thing. And that thing that you maybe didn't name before, it's actually like the bytes cross this bus. And this is actually why you get ambushed when it comes to integration. So what happens usually like, and yeah, I I also like fall into that trap before, which is like you wrote them as four separate targets, and but in reality they were always just like one thing if we're gonna render them down to first principles. And the one thing that gonna fix this is like by the shape that you're gonna choose. So all this depend on the bus bandwidth. And now like for the tail, and like if we're gonna talk about the worst case latency, it's also like the same truth here, just like in just we're gonna talk here about time instead of size. So like your inference doesn't take one fixed amount of time, just like take spread. This is like the distribution here. And because like the bus is actually shared between different things, so what that means like other things also like want to go through. And when they like contend for it, you just like need to wait longer. And that's like why it's got bursty. So here's like the average like maybe like comfortably was gonna be like inside your actual budget. And here's the actual deadline. And I want you just like to look at the tail here. So basically like spilling past it, the red part here is the time that you're gonna miss. And now here's the actual part that changes how you gonna work this out. So basically, like you can pull the average down by making your model smaller, maybe like using fewer bytes. But the issue like with the tail is like the tail is actually set by contention, which means like by what else is actually like fighting for the boss at the instant. What actually fights to move its actual byte to the next step. And for this one, like you cannot fix contention by just like shrinking your AI model, So the tail just like lives in a different layer than the actual model is. And for this one, it's actually like a system problem, not an AI model problem or machine learning problem. So for that's why like the reason why like most teams who only just tune the model will never fix their worst case scenario. And that actually falls out of so basically like just like falls out of one bandwidth constraint. So in other words, like just to summarize this point, like compute was never your bottleneck. So also so budget bytes. It's not about math here, and also like the four goals that are just like one quantities. They're not actually four separate goals. So just like the sides up front, which ones you're gonna spend your time and energy on. Also, like the tail is contention here, not the model. So basically, you need to control the what shares the boss and spec to avoid the worst case, and never take the average for granted. And also, like the pipeline moves bytes too. So the pre and post processing. So what you need to do is like you need to measure the whole thing, like the whole chain on the real hardware, not just measuring the model on your laptop and call it, well, we reached 99% accuracy, because that does not mean anything when move it to the edge. And yeah, now let's move to the next consequence. For the next consequence is actually this is like the one that ties this like everything that we talked about so far together. So the model is not overconfident. Like basically, like the model's overconfidence isn't actually flaw that someone maybe left in. Uh, the reason of it is actually the training objective, um, which will like worked exactly as designed. So it's like a design issue here. And let me show you exactly like why from the law's perspective. So this curve is like a representation of the loss, the thing that basically like the training gonna push down. And along the bottom here is how confident the model is on an answer that's already correct. So here's the model at 70% confidence. So the answer is already right, just like it got it, but I want you to look at the loss here. So it's still like high, and the slope is still actually steep. So training just is gonna keep pushing this down like this way toward 99%, because like the loss never stops rewarding more confidence. And that's there's like no floor to stop. So it's not gonna go down, like just never goes just like good enough. Yeah, you're right, just like relax, that type of actions. So what's gonna happen, just like gonna keep pushing toward more certain confidence, which in reality is gonna take forever. So basically it's useless. In other words, like the model is driven to extreme confidence by construction here, not by some accident. This is like a design issue in the first place. So the reason of that is like the objective is literally shaped to make it that way. It's just like rewarded to act that way. Now, like the other half, where does that objective say anything about inputs the model? That where does that say about it? That the model won't actually see in the actual training. So here's like the training data with defined loss landscape over it. So the training has an opinion about like every point in here, and here's like everywhere else, like every input the model will just like meet in the field that isn't like the actual training data, so it's different. And I wanted to look at it here. So basically it's blank. So nothing like in the loss would ever references this specific region, because like the training never looked at things that are even like resemble similarity here, because like there was no data here in the first place. So what's gonna happen is like the model's confidence here is not actually wrong. Uh, it's just like undefined. So in other words, like nothing ever shaped it to understand this thing. So like what's gonna fill the blank space is the same extrapolation geometry from consequence ones. So they're like flat rules, just like continued out into a space that nobody anchored. So like out here, the model is just like confidently applying an anchored rule and just like calling it certainty. So mm, based on that, what's gonna happen is like just like gonna produce some bullshit results, and just like we're gonna call it reality. So like here's the whole video in just like one line. So there are two different objectives here. First one is like knowing the answer, and second thing is like knowing whether you know the answer or not. These two are two separate things. So for like standard training, what it's gonna do is like it's gonna optimize the first one. So okay, so the standard training actually optimizes the first one, and that's like what all the efforts goes into. But in reality, like most likely that nothing would actually goes into the loss optimization for the second one. So in other words, like nothing ever like taught the model what unsure actually should feel like, because it's only ever like saw data with known answers. So the model certainty is not evidence of anything here. It's just like the output of a thing that trained to look certain, and that was never trained to was never trained to know when it's should not be certain. And like any system that was gonna treat that certainty as evidence has already made the deepest mistake in the whole field. It's just like mistaken the absence of a single of a signal for the actual signal itself. So the decision isn't about design choice here. It's actually forced. So the model is gonna always says like it's sure. It cannot be like it cannot be the thing that decides whether to act on its own answer from now, because it has like no real sense of its own uncertainty. So it's gonna always like tell you it's confident either way. So the decision to trust it has to live somewhere outside that model itself, and that's like the whole idea here. Not add some like safety features, because like something above the model has to own the question of when its answer get is gonna get used or not. And that thing should have um, like three moves when the answer looks shaky. Is either gonna act on it, or gonna hand it like to a human, or either like gonna refuse and just like drop to a safe state. So like these three decisions, and what's gonna trigger each of these, that's like the whole architecture and the system design of any system should be about. So if also like if the deadlines is too short for human, then maybe that's fine. Yeah, the fallback of this is gonna become an automatic safe state instead of person, but the requirement still like here does not move. So if anything if nothing like sits above the model to decide, then you don't have a system. You just like have a model that will eventually be confident and wrong. and on top of that, like nobody watching it. So what's gonna happen is like it's gonna like create a disaster. And now, let's step a little bit back because you've been looking at just like one thing the whole time here. So geometry fit to data control actually like represent what never learned, and like that's the center of this whole thing. And like the four consequences that we talked about are just like that one fact, just like seen from four different sides. So extrapolation is just like the geometry past data. Discarded features just like the geometry beside the discard features is just like the geometry beside the data, just like in space that you can't see. The shared bus is the actual physics underneath the computations, and undefined confidence is just like the geometry where it like never trained. So basically, it's just like same fact, which just like the four different phases. So that's why these aren't four different tips here. They're just like four shadows of one thing. So that thing is like the model doesn't know where its own knowledge ends, and because the end of its knowledge is exactly the place it has, like it had no data to learn from. So that thing is cause a lot these type of problems. Now like why now the question is like why no like nobody else, like why not, like why doesn't like everyone already know this thing. And the reason of this is like basically like the cloud is gonna hide all of these four faces. So let's start by talking about extrapolation drift here. So if we're in like in a cloud environment, then you're just like gonna retrain and redeploy tomorrow. For better pre-processing, you just like catch it in monitoring next week. Maybe like a blown computation budget, then you're just like gonna add bigger blocks. Um, and for confident and wrong, just like a human can notice that on a dashboard tomorrow morning. So basically, like every one of these is invisible when you have like second chance to review it, and even like when the model is wrong, it does not cause like disaster, either like on resources, people's lives, stuff like that. So just like need like to retry, you rerun, and just like the human can check it later, and that's like what hides this actual problem from them. And so basically, like if you're gonna take the second chance away, then all of these four problems are just like gonna stop. If you just like take that like retry the second chance away, then all of these problems are just like gonna stop hiding at once. And that's like the whole video here, not like talking about four different problems. We're just like talking about one condition with in like a no do over environment, and like just like the fourth thing that what was always there finally became visible in that environment. And now like the maybe obvious objection here is like especially like if you're a technical person, which is like the constraints are dissolving, is that right? So technically, basically like the ships are getting better every single year. Models are getting smaller. Like connectivity gets better everywhere. So does that means like these expire? Um, the answer is like if you're gonna go back to the four of the consequences, none of them is about how much computation you have. So geometry that extrapolates past this data that's just like math. It's not gonna change tomorrow, even like with more computations or bigger model. Feature space that you cannot see, that's also like pure math here. Confidence that's undefined of distribution, that's also like a math. So the one that touches hardware, the only thing is like maybe the shared bus, which may guess higher ceiling every year. But if we're gonna talk about detail, it's still like there will still be like contentions, and it's not gonna become zero by tomorrow. So in other words, like the ship gonna like gets easier, that's for sure. But the math doesn't move at all. It's always gonna be the same. So in other words, these issues won't gonna expire tomorrow because it was never about the hardware in the first place. Now, like, let's finalize this video. So a model that can't represent the limits of its own knowledge, that's a fact thing, like it cannot do that. And because those limits are exactly the place that had no data to learn from, that's the reason. So now, like, when someone shows you a model, what you should do is you shouldn't like just ask about how accurate that model is. What you should ask about is like, let me move this a little bit down. Oh, let me move to this other side. Okay. What you should ask about is like what distribution that number is actually on. Also, you should ask like whether the field input is close in feature space, or maybe just like close in pixels. Also, like, you should ask what the worst case is on the shared bus, not the average case. And also ask what sits above the model when its confidence stops meaning anything in the first place. So these four questions come straight from the geometry. So they're gonna tell you in a minute whether someone actually built a reliable system, or whether like your system that you're gonna deploy is reliable, or just like maybe you just like trained the model and you still don't have a reliable system yet. So basically, these are just like decade of doing this and capturing patterns given to you just like in less than 1 hour. So you can take it now and work out your own case. Like, that's the whole point here. And if you need any more additional help, or if there's like any technical issues in your system, and you want me to personally check your system and maybe give you some points, or maybe like you want to work with me, you can find my email attached like in the video description. And that's it. That's the whole video here. Take care and see you in the next one. Bye.